What's up? I'm Vin, and today I want to go through the 1998 AP Calc BC multiple choice. So we're starting here with question 1, and the first thing we want to answer is, for what values of x is the function f of x increasing? So if we want to find out where f is increasing, we're going to use the first derivative test. So we're going to start by taking the derivative of f of x. So we're using the power rule. We have 3x squared plus 6x minus 9. And now we want to set the derivative equal to 0. So we're looking for when is 3x squared plus 6x minus 9 equal to 0. And we can just divide everything by 3 here to make this a little simpler. We'll have x squared plus 2x minus 3 equals 0. And now factor this to x plus 3 times x minus 1. So the roots are going to be negative 3 and positive 1. So we take the roots and we throw them on a number line here. And this is a number line for f prime. And the shortcut here is I visualize this derivative. And if we notice, the function for f prime is a parabola with a positive coefficient in front of the x squared. And if the roots are at negative 3 and positive 1, this is what I'm imagining. But what I notice about this when I think about it is that the graph starts off positive. So this is a graph of f prime. We have the graph is positive, negative, and then it goes positive again because it goes from over the x-axis to under, back over. So that tells me how the signs are going to work out for each interval here. Another way to assign the plus or minuses here would be to plug in test values. Like let's say I plugged in 0 to our first derivative. I would have 0 plus 0 minus 9, and this works out to a negative, so that's why this interval is negative. But this method is a little bit faster to just visualize the graph. And we want to know where is the function increasing. So what this tells us is we're looking for where is f prime greater than 0. And that's going to be on this first interval and this last interval here. So that's going to be from negative infinity to negative 3 and also from 1 to infinity. But notice the way they wrote the answer choices here, we have x is less than negative 3 or we have x is greater than 1. So the first question here, our answer is going to be choice C. So for question 2, we have parametric equations for x and y, and we're on the interval from negative 3 to 3. And we're told here the graph of these parametric equations is a line with a slope. So if we want to find the slope of this line, just know that dy dx is slope in calculus. That, the derivative tells us the slope of a function. But in the parametric world, dy dx is equal to dy dt divided by dx dt. So that just tells us we have to find what is dx dt and dy dt. So using these pieces here, dx dt, the derivative of 5t plus 2 with respect to t is just 5. And then dy dt, the derivative of 3t with respect to t is just 3. So then if we just make this substitution here, dy dt is 3, dx dt is 5. And this tells us that the slope is going to be a choice A, 3/5. So a question like this is just very tedious. We want to find the slope of the line tangent to this curve at the point x equals 2, y equals negative 1. So we're going to use implicit differentiation here. And just know anytime we take the derivative with respect to x of something like y squared, what we want to do is take the derivative with respect to y of y squared and then multiply by dy dx. So this individual piece would work out to 2y dy dx. The shorthand way, though, is just knowing that anytime you take a derivative of a y term, that it's going to tack on a dy dx or a y prime. So we start this off. The derivative of y squared is 2y dy dx. And now we have plus, and now we're going to use the chain rule. We're doing the derivative of the outside, so we have 3 times xy plus 1 to the second times, and now we have to do the derivative of the inside. And to take the derivative of the inside, the derivative of x times y, well, we do the product rule. We have the derivative of x is 1 times y plus x times the derivative of y is 1 dy dx. So just know for implicit differentiation, anytime you take the derivative of something with y with respect to x, there's just going to be that extra piece at the end. And now we did the product rule on xy, we have plus the derivative of 1 is just 0. And now this is equal to the derivative of the right side is just 0. So now we can just clean this up a little bit, and we have 2y dy dx plus 3 times xy plus 1 squared. And then in the brackets here we have y plus x dy dx. And this is all equal to 0. Now we could solve for dy dx, but what I like to do with this step is just plug in. You have x equals 2, y equals negative 1. So if we plug in here, see I have 2 times negative 1 is negative 2. So I have negative 2 dy dx plus 3 times, and now I have x times y. X times y, I have 2 times negative 1. So that's negative 2 plus 1, and that's being squared. And then y is negative 1, and we have plus x is equal to 2 dy dx, and this is all equal to 0. So now we just have to simplify things, but notice negative 2 plus 1 is equal to negative 1, and negative 1 squared is positive 1. So this is negative 2 dy dx, and now we have 3 times positive 1 after we do negative 1 squared, so we have plus 3 times, and we have negative 1 plus 2 dy dx equals 0. We'll just make this y a little bit neater. Okay, so we'll just finish the rest of this over here. Now we have negative 2 dy dx, and now we're distributing this 3. We have 3 times negative 1, and then 3 times this piece. So 3 times negative 1 gives us minus 3, and then we have minus 6 dy dx equals 0. So now we combine these terms here. Notice what we have. We have negative 2, and I'm sorry, this is a positive 6. Let me just correct this. We have positive 3 times positive 2 is positive 6. So just a little arithmetic misstep there, but we corrected it here. So we have negative 2 dy dx plus 6 dy dx. That's going to give us 4 dy dx minus 3 equals 0. And if we solve for dy dx, and this is specifically at the point 2, negative 1, is going to be equal to 3 over 4, which is going to be choice D. So that is our solution to question 3. So for this next question here, the first thing that jumps out at me is that this fraction, the term on bottom is factorable, and it breaks up to x minus 4 times x minus 2. And once you have an expression like this that has 2 factors on bottom and this constant on top, you could use partial fractions and break this up as a over x minus 4 plus b over x minus 2. So now the approach shifts to solving for the values of a and b. A and b are constants. So the first part here, I would have to multiply by x minus 2 over x minus 2, and the second part I would have to multiply by x minus 4 over x minus 4, because now these two fractions have the same denominator, and that denominator matches the fraction on the left. So now that we have all 3 fractions with the same denominator, in a sense all the denominators could cancel, and now the numerators could be set equal. We have 1 equals a times x minus 2 plus b times x minus 4. And from here, if we want to solve for a and b, the easiest way to do this is to just plug in test values. If we plug in x equals 2, that gives us 1 equals a times 0 plus b times, and if we have x equals 2, we have 2 minus 4 is negative 2. And now the resulting equation here, after this cancels, is 1 equals negative 2b, which tells you that b is equal to negative 1/2. And now next, we could plug in x equals 4. And if we plug in x equals 4 to this equation here, we have 1 equals a times 4 minus 2 is 2 plus b times 4 minus 4 is 0. So now this time around b cancels out, and it gives you 1 equals 2 times a, which gives you a equals positive 1/2. But now this algebra that I showed in red, I often just do that in my head, and that helps me solve for a and b. So I'm going to erase the algebra that I showed originally, because now this information here, the a value and the b value, allows us to take this original integral and break it up into 2 separate integrals. So we could say this is now equal to, we have a over x minus 4. So a I'm just going to factor out in front because it's a constant, and we're going to have dx over x minus 4, and b is equal to negative 1/2, so we'd have minus 1/2 the integral, and we have dx over, and b was attached to the factor x minus 2. So now these 2 individual integrals are much easier to evaluate. This we could just use the natural log technique for integration here. I could go through the trouble of doing a u substitution, say something like u equals x minus 4, but anytime you have du equals 1 times dx, that means you could skip doing u sub and just do the antiderivative straightforward. So we have 1/2 times natural log absolute value x minus 4 minus 1/2 natural log absolute value x minus 2. And of course, don't forget the plus c at the end, because this is an indefinite integral. And then you look to the answer choices here, and you'll notice that our answer isn't there, and that's because we have to know a little bit more algebra. And the trick here is to group these 2 together, that you have 1/2 times natural log of this term minus natural log of this term. But just know, anytime I have something of like natural log of m minus natural log of n, I could combine these into a single log using this property here. So that's what we're going to do. We have 1/2 times natural log, and we're going to have absolute value x minus 4 over x minus 2. We close the absolute value, and then we have plus c here. I didn't need this extra parenthesis, but just know this is going to match with choice A. This is our solution to question 4. All right, this question here is just kind of tedious. This, we're just finding the second derivative of h, and h is just in terms of this composition function here. So we're going to use the chain rule. We have h prime is equal to, we have the derivative of the outside is f prime. We keep the inside the same, and then we multiply by the derivative of the inside, which is this. But now, to take the second derivative, this is where it gets really annoying. We're going to have to use the product rule. And if we're using the product rule, we're saying u is equal to this term, and v is equal to this term. So if we want to show that on the side here, we're saying u is equal to f prime g of x, and v is equal to g prime of x. So to use the product rule, I have to find out what is u prime. So I do the derivative of the outside, and the derivative of f prime is f double prime at g of x, and then times the derivative of the inside is g prime. And then v prime would just be g double prime of x. So now, if I want to evaluate what is h double prime, I'm just doing u times v prime plus u prime times v. So I have f prime of g of x times g double prime of x plus, and now I have u prime times v. So I have f double prime g of x times g prime, and then times v. V is also g prime here. Well, the last two terms are going to match. So if we combine the like terms here, we have f prime g of x times g double prime of x plus f double prime of g of x times, and we'll put a bracket here, g prime of x squared. So now we just have to match this to an answer choice, and this looks like choice A. Notice the commutativity of addition, like they have this thing written first, but we have f double prime at g times g prime squared plus f prime g of x g double. So choice A for question 5. Okay, for this question here, we have a graph of h of x. So I'm just going to write h of x over the graph here. And we want to know which of the following answer choices could be a graph of h prime. So all of these are potential graphs of h prime. And the trick to these questions is to use the idea that the derivative tells you if a function is increasing or decreasing. So what I first notice here is that h is, and I'll abbreviate, h is increasing from here to here, and then h is decreasing from about here to here, and then h is increasing again. So what this means in derivative language is that h prime is going to be positive, negative, and then positive again. Okay, because once again, the derivative, the first derivative tells you if your function is going up or down. And if the function is increasing, that means your first derivative is positive. So now I look at the answer choices and say, which graph goes from positive to negative to positive? Well, this one here only goes from positive to negative, so that's why this answer is out. This one goes from negative to positive just once, so this one's out. This one goes negative, positive, negative, so that doesn't match what we need to. But if you notice here, we have positive, negative, positive. We have positive, negative, positive. So these two are left. Now, the next thing that I notice is concavity, that a graph that is concave up is going to look like this, like it's smiling at you. And a graph that's concave down is kind of frowning at you like this. So this graph starts off concave down because it's frowning. So the graph goes from concave down to concave up. Okay, so what that means for us is that concave down means that f double prime is less than 0, which means, and concave up means that the second derivative is greater than 0. But now we just have to think, what is the connection between the second derivative and the first derivative? Well, if I want to look for where my second derivative is negative, this happens when my first derivative is decreasing. And in this scenario, my second derivative is positive when my first derivative is increasing. So what this tells us, if the only switch here is that the graph goes from concave down to concave up once, that means we need a scenario where our derivative is decreasing and then our derivative is increasing. So that's why it has to be choice E, because the graph starts off decreasing and then it goes to increasing. Choice D is no good because the graph goes from, the derivative is increasing, which means concave up, then it's decreasing, which means the graph would be concave down, H, and then the graph of h prime is increasing again, so the graph would go back to concave up, and then it decreases again, it would go back to concave down, which doesn't make sense here. And disregard that I'm using f instead of h, but the idea is the same no matter what they name the function, but it's going to be choice E for question 6. So for question 7, sometimes the trickiest part of an integral is just knowing what algebra to do. So my first instinct here is when I have an expression like this, is breaking this up to x squared over x minus 1 over x. So splitting that fraction apart, and if we simplify here, this is now the integral from 1 to e, x squared over x is x, and then we have minus 1 over x, and we tack on the dx. So we're using the fundamental theorem of calculus part 1. So we have 1/2 x squared, that's the antiderivative of x, and then minus natural log absolute value of x, and this is being evaluated from 1 to e. So now we just plug in, we've got 1/2 e squared minus natural log absolute value of e, minus, and we plug in 1, we got 1/2 1 squared minus natural log, and the absolute value of 1 is just 1, so I'll leave it like this. Now natural log of 1 is 0, so this is going to cancel out. So what we have is we've got 1/2 e squared minus absolute value of e is just e, and natural log of e is 1. And then we have minus on the inside of the parentheses, 1/2 times 1 squared is 1/2. So just think of this as 2 over 2. So that when we simplify this, this is 1/2 e squared minus, and we have minus 2 minus 1, giving us minus 3 over 2. So our solution here, let's now just find it. Question 7 works out to choice E. So we're up to question 8 here. We have a derivative, sine x cosine squared x. We have an initial condition here, and we want to know what is the value of y when x equals 0. So just do a little separation of variables for this one, and we're going to solve for y. So we have this derivative, we're going to multiply both sides by dx. And now that's going to tell us that y is equal to the integral of sine x cosine squared x dx. And let's just make that much nicer. Okay, so there's sine x cosine squared x dx. And to work this one out here, we're going to use a u substitution. So we have u is equal to cosine x, which tells us that du is equal to negative sine x dx. And what I like to do for these questions is I'm going to solve for the leftovers. I want to get sine x dx by itself. So I'm just going to move that negative over, and that gets us here. So then we make the substitution. We could say that y equals, and we have the integral of cosine squared x. That entire piece I could just say is u squared. So that's going to tell us cosine squared x is just u squared, and the leftovers sine x dx is equal to negative du, this piece over here. So I'm just going to tack on the negative du. So we completed the u substitution, but now we just have to do the antiderivative. So we have negative 1/3 u to the third plus c, and now I'm going to plug in for u. Y equals negative 1/3, and we have cosine cubed x plus c. But now, once again, we're using the initial condition that the point pi over 2 comma 0 is on this curve. So if we just plug in y equals 0 equals negative 1/3, and we have cosine cubed at pi over 2 plus c, we'll just know cosine at pi over 2 is 0. So this tells us that c is equal to 0. So our our particular solution, this is our general solution, but our particular solution here is just y equals negative 1/3 cosine cubed x. And what we want to do is, what is the value of y when x is equal to 0? So when x equals 0, that gives us y equals negative 1/3 cosine cubed at 0, and cosine of 0 is 1, so this is just going to work out to negative 1/3. So our answer to question 8 is going to be choice B. Now for this word problem here, we have the flow of oil in barrels per hour through a pipeline on July 9th is given by the graph shown above, and we want to know which of the following best approximates the total number of barrels of oil that passes through the pipeline that day. Well, the whole idea in this question is we want to find the area under the curve. Because just know, for any one of these pieces we find the area of, the units on the y-axis are barrels, which I'm just going to abbreviate like this, per hour. And along the x-axis, the units are hours. So notice what happens when we multiply barrels per hour times hours. The hours cancel, and it gives us just barrels, which is what we're trying to find, the total number of barrels. And of course, for area, we're doing base times height. So that's just kind of the concept behind why we're finding area in this case. So the trick behind this is that each of these units, like we're going over 6 and we're going up 100. So if I have a rectangle that's 6 wide by 100 high, that means this is going to work out to 600. From 6 to 12 is also 6 across, and it's going up 100, so this is also like this piece is also going to have an area of 600. Same thing with this one here. From 12 to 18 is 6, and we're going up 100, so this is 600, and this is 600. And now this piece up here is the only tricky part, but just know, I think we see by now that each of these little rectangles has 600 barrels of oil if we're like thinking about what we're measuring here. So if we cut it in half, this piece is going to be 300, and this piece is going to be 300. So what we have is we have 600 times 4 plus, and then we have 300 times 2. So this works out to 2400 plus 300 times 2 is 600. So altogether we have 3,000 barrels of oil. Oh, that's our approximation here. So 9 is going to be choice D. So for this question here, we're told the position of a particle, the x and y. So if I want to name the position, let's say P of t, as a vector here, we could write this as t to the third minus t, comma, and then we have 2t minus 1 to the third. And what we could find next, because we want to ultimately find the acceleration vector at t equals 1, we could find the velocity vector. And to do that, we have to take the derivative of position. So we're taking the derivative of the x component and getting 3t squared minus 1. And to find the derivative of the y component, we have to use the chain rule. So we're doing the derivative of the outside using power rule, and then the derivative of the inside also using power rule gives us 2. So we could simplify this velocity vector as 3t squared minus 1, and then 3 times 2 in front is going to give us a 6. We have 2t minus 1 to the second. So now the acceleration vector, we're doing the derivative of each component again. We have, well, we'll focus on this one here. The derivative of 3t squared minus 1 is just 6t. And now on this part here, we have 2 times 6 is 12. We have 2t minus 1 to the first, but we have to remember to do the derivative of the inside, which is 2. So our acceleration vector is 6t, comma, and then we have 12. I'm sorry, let's actually multiply the numbers together. We have 12 times 2 is 24 times 2t minus 1. So what is the acceleration vector at t equals 1? We just substitute in t equals 1, and now we have 6 times 1 is 6, comma, and then we have 24 times 2 times 1 minus 1 is 2 minus 1, which is 1. So here is our acceleration vector. So for question 10, we have choice E. Now some of these questions here are so easy that they're difficult, but we have f of x is a linear function. So I'll just write it as mx plus b. And we want to find the definite integral from a to b of f double prime of x. Now, if this one is not obvious that it's 0, just know if my function is linear, that means my first derivative is constant. So if I find a second derivative here, the second derivative of a linear function is 0. So that means we're doing the integral from a to b of 0, which is just going to work out to 0, because just know a definite integral tells you the area under the curve. So if your curve is the line y equals 0, and we're going from a to b, no matter where a and b are, think of this as a rectangle that has no height, so it's going to have 0 area. So this one's going to be choice A. So for this question, we have a piecewise function, and we want to find the limit as x approaches 2. Now, notation is not as important, so for here, what I do is I look for the left side limit and the right side limit. And if I'm on the left side of x equals 2, that means I'm looking at scenarios where x is less than 2. Or I could even say x is less than or equal to 2. And if I'm on the right side of 2, I'm looking for values of x that are greater than 2. So that tells us when I want to find the left side limit that I'm going to use this piece here. So this tells me the limit as x approaches 2 from the left of f of x is going to use the piece natural log x, because once again, if I'm on the left side of 2, I'm on this interval here from 0 to 2. And if we want to evaluate this limit, we just plug in. This is going to give us natural log of 2. So that's our left side limit. If I take the limit as x approaches 2 on the right side, now I have to look for the piece where x is greater than 2. And just know the statement 2 is less than x has the same meaning as x is greater than 2. So that's why we're going to use this piece here. We're using the x squared natural log 2 piece. And to evaluate this limit, we do it just by direct substitution. We plug in x equals 2, and we get 2 squared natural log 2, which gives us 4 natural log 2. But notice that the left and right side limits are not equal. So the limit as x approaches 2 on the left of f of x is not equal to the limit as x approaches 2 on the right of f of x. And anytime your left and right limits are not equal, that means the limit in general is non-existent. So it's going to be choice E. So what we have for this question here is we have a graph of the function f, and we're told that there's a vertical tangent at the point 2, 0. So this is going to be important in a moment, that we have a vertical tangent line here. And we have horizontal tangents at 1, -1. So that's over here. We have a horizontal tangent. And we also have a horizontal tangent here at 3, 1. And we want to know for what values of x between -2 and 4 is f not differentiable. So what we have to look out for here is we need to look out for sharp turns. We need to look out for vertical tangents. And we have to look out for points where the function is not continuous. So we could say like points of discontinuity. So that is a big idea for this type of question, that you have to know what it means for a function to be not differentiable in terms of its graph. So if we look here, notice there are no sharp turns. So like this one does not show up anywhere. Vertical tangents, they told us that we have a vertical tangent here at x equals 2. So far we have f is not differentiable at x equals 2. So that's one value. The next thing to look for here is points of discontinuity. And notice that f is not continuous at x equals 0. So this is discontinuous at x equals 0. So that tells us that these are the two values here. It's going to be choice B. The trap in this question was the fact that they told us that we have horizontal tangents at x equals 1 and x equals 3, but this just means that the derivative or the slope is 0. So if I had to make a statement here, I could say that f prime of 1 is equal to 0, and also f prime of 3 is equal to 0. Horizontal tangent means 0 slope, but vertical tangent means no slope. So for a question like 14, this question has potential to be easy if you show up to the test knowing your Maclaurin series for simple functions like sine x, cosine x, and e to the x. So here we want to use the 5th degree Taylor polynomial about x equals 0. But just know a Taylor polynomial centered at 0 is the Maclaurin series, or Maclaurin polynomial. So we have sine x equals x minus x to the 3rd over 3 factorial plus x to the 5th over 5 factorial. And it would be minus x to the 7 over 7 factorial. And that's the pattern. It's all the odd powers of x. But if we're using a 5th degree Taylor polynomial, that means we're stopping it here. We're only using this part. So if we had to name it, let's say t5 of x, this is just going to be equal to x minus x to the 3rd over 3 factorial plus x to the 5th over 5 factorial. So if we're going to use this to approximate sine of 1, we could say sine of 1 is roughly equal to 1 minus 1 to the 3rd is just 1. So we have 1 over 3 factorial plus 1 over 5 factorial. And notice in the answer choices, they actually expand the factorials. So we have 1 minus, just know 3 factorial equals 3 times 2 times 1, which is equal to 6. So we have 1 minus 1 over 6 plus, and if we do 5 times 4 times 3 times 2 times 1, that's going to give us 120. So we're looking for this answer choice, and it's choice E. So for this next question here, we're using integration by parts, and the x in front of the cosine x is what gives it away for me. And the trick to remembering the formula, if we know the product rule, the derivative of uv prime is u prime v plus uv prime. If we know this formula, we could use this to remember the formula for integration by parts. So this is if you forget the formula. And the way we get to the formula for integration by parts is we do the antiderivative of everything involved in the product rule. Now the antiderivative of uv prime is just uv, because the derivative and an antiderivative kind of just cancel out here. And this is going to be equal to v I'm going to leave alone, but u prime I'm going to rename du. And then we have plus u times v prime, and v prime we're going to call dv. So this is starting to resemble the formula for integration by parts. The only thing that we're doing is now we're going to solve for this expression. So we have u dv in the integral is equal to uv minus the integral of v du. So we're just subtracting this to the other side. And now all we have to do here is define our u term, which in this case u is going to equal x, and then our v term, our dv term is going to be cosine x dx. Now a little trick to knowing which one is which, like how do you know which one to make u and which one dv, is the phrase liate, where this stands for log functions, inverse trig functions. A is algebraic, t is trig functions, and e is exponentials. So notice this is an algebraic and a trig function, which is over here, but the algebraic function outranks the trig function. So that's why the algebraic function x becomes u. So here what we're going to do is we're going to make this setup over here. We have u is equal to x, and we have dv is equal to cosine x dx. And from this tells us what du is. Du is the derivative of x, which is 1 dx, and now we use this to find v. V is the antiderivative of dv, and the antiderivative of cosine x dx is sine x. So now we make the substitution. U times v is x sine x, and then we have minus v times du is sine x dx. So now we just have to take the antiderivative of this piece, and then we'll slap on the plus c at the end. We just can't forget that. So we have x sine x. And think about this very carefully. The trick to knowing the antiderivative of sine x is, I think, in terms of derivatives. The derivative of cosine x is equal to minus sine x. So if I want to find the integral of positive sine x, it's going to be minus cosine x. So I have minus cosine x plus c. Okay, so once again, just think in terms of the derivative. The derivative of cosine is negative sine. So the integral of negative sine is positive cosine. Or I could say the integral of positive sine is negative cosine. But the minus minus is going to change to a plus sign here. So I could just say that our final answer is going to be x sine x plus cosine x plus c, which is choice B. So for question 16, it's all about really knowing your vocabulary and your theorems. And what we need to know here is when we want to find points of inflection of a function, this tells me right away that we need to investigate the second derivative and look for a second derivative sign change. So to start this, we're starting with f of x. We want to find the first derivative, which is going to give us 15x to the fourth minus 20x to the third. And then this is going to tell us the second derivative. So we're using the power rule straight across here again. So we have 60x to the third minus 60x squared. And now we want to find the zeros or the roots of f double prime. So we set this second derivative equal to 0. So we have 60x squared times x minus 1 is equal to 0. And this gives us x equals 0 and x equals 1 as the roots. But there's a very dangerous trap for this question. Some people, when they go through these questions very quickly, just assume that there's going to be sign changes all the way across. And they say 0 and 1. But this is a very dangerous trap here because the fact that this piece here is x squared, 60x squared, this factor is always positive. So if I were to plug in test values, let's say f double prime of -1, and then I plug in f double prime of a half, and then f double prime of 2, if I plug in something like -1 to our second derivative, I'm going to use this factored form here. That's going to give me something positive, and then if I have -1 minus 1, that's going to give me something negative. But watch what happens if we plug in. So this is going to be less than 0 if I plug into the second derivative. But if we plug in something like 1/2, notice 1/2 works out positive because I'm squaring it and multiplying by 60. But when I do 1/2 minus 1, that works out to something negative, and a positive times a negative is negative. There's no sign change at 0. So this is very big. There's no sign change. So there's no point of inflection at x equals 0. But now if you plug in something like 2, notice I have 60 times 2 squared is positive. 2 minus 1 is positive, and a positive times a positive is positive. So I have 1 point of inflection at x equals 1. So that tells us here, what are all the x coordinates? We have a point of inflection. So we have a point of inflection, I'll just abbreviate, at x equals 1. So that is our answer, choice C. 17 is a good question because it tests you on a lot of things all in one question. So here we have to order f of 1, f prime of 1, and f double prime of 1. Well, if this is a graph of f, so this is the graph of f of x up here, f of 1 is just the y value. So this is just going to be equal to 0. Now when I want to look at f prime of 1, f prime of 1 tells me the slope of the tangent line. So if I just draw this in very carefully here, if I looked at a tangent line, we'll just make that a little bit neater. The tangent line here, I could just say that f prime of 1 is greater than 0 because the tangent line is going up. So f prime of 1 is positive, and then f double prime of 1 talks about the concavity of the graph at x equals 1. But notice this graph is kind of frowning at us. It's the upside down smiley face here. So what this tells us here is that the second derivative at 1 is going to be less than 0 because the curve is concave down. So now we just have to order this. So the smallest one is going to be the negative. So f double prime of 1 is the smallest. The next smallest one is going to be the 0, which is f of 1. And then the biggest value is going to be the positive, which is here. So now we just have to match this to the answer. We have f double prime is the smallest, then f of 1, then f prime. So 17 is choice D. So for question 18, we just have to know all of our convergence and divergence tests. We want to know which series converge. Now, the first thing that jumps out at me for Roman numeral 1 is that if we take the limit as n goes to infinity of the general term here, n over n plus 2, notice here that this limit is equal to 1, which is non-zero. So by the nth term test for divergence, we could say that this series diverges because the limit of the nth term has to go to 0, and 1 is not 0. So that one's out. And if we look at Roman numeral 2, this one is a good series to look at because we have to plug in a few values here to really see what's going on. So if I plug in n equals 1, n equals 2, n equals 3, and then add them, notice we have cosine of 1 times pi over 1 plus cosine of 2 pi over 2 plus cosine of 3 pi over 3, and this just goes on and on. And if we make the substitutions here, cosine of 1 pi is negative 1, and then we have cosine of 2 pi is positive 1. And then if I go to cosine of 3 pi, I'm back at negative 1 here. And you can start to see the pattern that it's negative 1 over 1 plus 1 over 2 minus 1 over 3 plus 1 over 4 minus 1 over 5, and so on, that this series does in fact converge. If we had to rewrite this in simplified form here, I could start with negative 1 to the n, because at n equals 1, negative 1 to the first is negative, and this thing starts negative. So I have negative 1 to the n over n like this. This is the same exact series as the original, and this is the alternating harmonic series, which does in fact converge. If you know your alternating series test, you could also use that here, but recognizing this as the alternating harmonic is a faster way to say it converges. But you could also use the alternating series test here. And now the third one here, this is the harmonic series, and the harmonic series diverges. Okay, you could also say p series here, and that the p term has to be greater than 1. So since p equals 1, p is not greater than 1, p is less than or equal to 1, so this diverges. So the only one that converges is Roman numeral 2, so we're going with choice B. Now this question is tricky because we're in the no calculator section, so you have to be able to sketch basic polar curves to answer this. And what we have here is the polar curve r equals 4 sine theta. The way this looks is that it goes 4 units up the x-axis, and it's a circle, so it's going 4 units up the x-axis. Let's draw this a little neater. And it also connects to the origin like this. So this is r equals 4 sine theta. And then r equals 2 is a circle centered at the origin with radius 2. So this looks something like this. So what they're actually asking for in this question is we want to find the area inside r equals 4 sine theta, but outside the blue circle. So if we have to stay inside the purple circle, but outside of the blue circle, that's going to put us over here. So what we need to know for this question is we need to know the formula for finding the area between two polar curves. And another thing is we have to know what are the limits of integration here. So we have to think about where does the region start and where does it stop when we're finding the area of whatever we have here in red. So to find out where these regions overlap or where they intersect, we're going to set these two equations equal to each other. So we set 4 sine theta equal to 2, and then that gives us sine theta equals a half. And sine theta is equal to a half when theta equals, and if you think in degrees, that's going to be at 30 degrees or pi over 6 radians. And also know that not only is sine positive in quadrant 1, it's also positive in quadrant 2. So in quadrant 2, we would use a reference angle of pi over 6, so that would be at pi minus pi over 6 here. So theta would equal, let's fix that. So theta equals pi over 6, and if you think of this as 6 pi over 6, the other angle is 5 pi over 6. So those are going to be the two angles involved, and something's telling me that's going to narrow it down to the other choices here. So we have choices C and D are the only ones left over. But now the idea is the formula is we have theta 1, theta 2, we have 1/2 outside, and we have the outside radius squared minus the inside radius squared d theta. So now just think about which function is on the outside. It's the 4 sine theta. So this is going to be 1/2 pi over 6 to 5 pi over 6. And now the outside function squared, if we square this, this is going to be 16 sine squared theta. So we'll just make that a little neater. And then we have minus the inside function squared. 2 squared is 4 d theta. So now we just have to match this. This looks like it's going to be choice D. Choice C is a devastating trap because the mistake here is that the student just does the outside function minus the inside function and then squares it, but you have to square them separately, then subtract. So this one's going to be choice D. Now this question annoyed me just for the wording, but they're saying here the rate at which the cube root of x is increasing. So that's the derivative with respect to x of the cube root of x. The word is in math means equals, so I could say equals 1 over k times the rate at which x is increasing is the derivative with respect to x of x. So now I just take the derivative piece by piece and just know the cube root of x is equal to x to the 1/3, and we write it like this so we could use power rule. So this is 1/3 x to the negative 2/3, and I'll just clean this up a little bit. Make sure that x doesn't look like it's in the denominator, it's out in front. So we have x to the negative 2/3, just doing the power rule here, equals 1 over k, and the derivative of x is 1. So from this step here, we could rewrite this. We have 1 over 3 x to the positive 2/3 equals 1 over k, and they're saying when x equals 8. So when x equals 8, that gives us 1 over 3 times 8 to the 2/3 equals 1 over k. And now I'm using power over root here. 8 to the 2/3, the cube root of 8 is 2, and 2 to the second power is 4. So this gives us 1 over 12 equals 1 over k, which tells us that k is equal to 12. So this is going to be choice E. So for question 21, we want to find the length of the path described by these parametric equations. So we just have to know our formulas here. And the formula for the length is going to be the integral from t1 to t2. We have a square root, and we've got dx dt squared plus dy dt squared. And then there's the dt on the outside. So now we just find each of those pieces on the inside. dx dt, we use the power rule, and we're doing 1/3 times 3t squared. That's just going to give you t squared. And then dy dt, using power rule, is going to give you 1/2 times 2t, which is just going to give you t. The coefficients cancel out pretty nicely. So that means the length is equal to, and they were nice, they gave us the time intervals here. It's from t1 is 0 to t2 is 1. And now we just plug in dx dt is t squared. So we have t squared squared plus, and then we have t squared like this with a dt. So if I just simplify this, this is the integral from 0 to 1. Square root, you got t to the 4th plus t squared dt. Now I just have to match this to an answer choice. That looks like choice C. That's going to be our solution to 21. So for question 22, we're using a direct application of the integral test. And for the integral test, if I had integral from 1 to infinity of dx over x to the p, then the way I would evaluate to see if this integral converges or diverges is I would evaluate this corresponding limit, which in the question they tell us that this limit is finite. So that means that this improper integral converges, it has finite area, which means the corresponding series from n equals 1 to infinity, 1 over, instead of x to the p, we're using n to the p, also converges. So this tells us the solution is going to be choice A. Now, for questions like this where the answer is really fast, I like to go through the other answer choices quickly to see that they don't make sense, that they're definitely wrong. So here, when they say that the series diverges, this would only be true if this integral was infinite. So B is out. Now, if I reduce the power of this exponent by 2, then the resulting series also converges. That's not necessarily true, because if I had, let's say, 1 over n to the 3rd, and I have that in a series, but I reduce it by 2, and I have 1 over n to the 1st now, this is the harmonic series which diverges. So that's why C is out. And the same argument could be held here for choice D, that let's say I start with something like 1 over n squared, reducing the power by 1 would give me something that diverges. So this one could be true, but it could also be false, like I just showed here. And now for choice E, what this tells us is that if this series converges, that means that P has to be greater than 1. So if I add 1 to this, that means P plus 1 would be greater than 1 plus 1. So P plus 1 would be greater than 2, and this would still converge. So this is a false statement here. If I increase the exponent here of this series, it's only going to converge faster. So that's why we have choice A. So for questions like 23, I like to draw these out to try to make sense of them. So what we have is, let's draw this a lot neater. We have some continuous function, and it's defined on the closed interval from a to b. So I'm just going to draw this out. And we're told here that f has a relative maximum at x equals c. So let's say c is somewhere in between. So c is between a and b. So if we draw this out here, so there it is, and let's say I drew this, let's draw this a little bit nicer so it really matches what we were just talking about. So here's the graph of f of x here. Which of the following statements, and the key word here is must be true. So f prime of c exists. Now, the way I drew it so that it was nice and smooth. But let's say I draw it a second way. And the key is you want to draw this in a way so that you try to make everything fail. And f of c is up there, but let's say instead of drawing it smooth, I do a nice sharp turn here at x equals c. So that would mean that f prime of c does not exist because of the sharp turn. But I still have a relative maximum here. Just know a critical point doesn't have to just occur where the derivative is 0. It could also occur where there's a sharp turn where the derivative does not exist. So Roman numeral 1 does not have to be true. But if f prime of c does exist, then the slope there has to be 0. See, that is true because we have a relative maximum at c. So if we have a hill at this location, that means the slope has to be 0 there. So this one is definitely true. And what we're told next is that if the second derivative at c exists, then the second derivative at c is less than or equal to 0. See, that one is going to be true because notice this curve on this little interval here is concave down. So because it's concave down at this local maximum, remember, if the second derivative does exist. So this means, since we're concave down here, that the second derivative here is going to be less than 0. But just know the second derivative test, you could also have a scenario where the second derivative equals 0, and you also have a local maximum or local minimum there. So the fact that they included the 0 was very important because, remember, you could have a scenario where the second derivative is 0 and you still have a local max or min. So choice 3, Roman numeral 3, is also true. Choice E is our answer. So for question 24, we have a slope field, and we want to know which of the following is a potential differential equation for this slope field. Now, what I like to do for questions like this is look for a pattern. And I notice in this part of the graph here, look at this diagonal. Notice here, all of the slopes are 0. So what this tells me is that if we're on the line y equals negative x, the slope at all of those values is equal to 0, because you see how all of these lines are horizontal. So now piece all of that together. If y equals negative x, dy dx has to equal 0. And when I look at the answer choices, this one jumps out at me, because if I let y equal negative x, that tells me I have dy dx equals x plus y equals negative x, and this is always equal to 0. If you use that idea for any of the other solutions here, it's not going to work out. Like notice here, like this is the point, let's say -1, +1, that if I plugged in x equals -1 here, I don't have something that's equal to 0. If I plug in, let's say x equals 1 for this one, notice I have something non-zero. So you could also get the other choices to eliminate, but I find that looking for this if-then pattern is the easiest way to evaluate these, and then you just match it to the answer choice. Okay, for question 25, this is just a very tedious question. What we have to do is we have to evaluate this improper integral, the limit as b goes to infinity of, and we have the integral from 0 to b of x squared e to the negative x cubed dx. So we have to evaluate this entire mess. My advice is to do the integral on the side and then plug back in. So I'm just going to treat this as an indefinite integral. I'm just looking at this part over here. And we're going to use a u substitution. U equals negative x to the third. So then du is equal to negative 3x squared dx. And since there's only an x squared dx left, I'm just going to solve for x squared dx. And that gives us negative 1/3 du equals x squared dx. So now we make the substitution. We have e to the negative x cubed, but remember that's u. And then x squared dx is negative 1/3 du. So this is negative 1/3 e to the u plus c, and this is negative 1/3 e to the negative x cubed plus c. But just know, over here, I'm not going to use the plus c because this is a definite integral. So now we switch back, and we did the antiderivative step just before. So we have the limit as b goes to infinity, and now we do the antiderivative, which is negative 1/3 e to the negative x to the third. And remember, the plus c we leave out because it's a definite integral, and this is going from 0 to b. So now we just complete this with FTC part 1, the fundamental theorem of calculus, and we're plugging in b, we're plugging in 0, and we're subtracting. Now for questions like this, I like to treat the constant, like I take the constant on the outside, and then I make the substitution and subtract. So I'm leaving the negative 1/3 outside, and we got e to the negative b cubed minus e to the negative 0 to the third. And we'll go ahead and get rid of this stuff here since we I already did the antiderivative, so I'm just going to make some space. So the rest of this will finish the question here in this space. So what we have, and let's just change colors so the work doesn't collide, is we have the limit as b approaches infinity. This is equal to, we have negative 1/3, and now this is 1 over e to the b cubed minus, and then this is e to the 0 when we have negative 0 cubed. So now we close this out, and this is going to give us, we evaluate the limit. We have negative 1/3, and then 1 over e to the infinity cubed is going to 0 minus 1, and now you have negative 1/3 times negative 1 is 1/3. So this works out to choice C. Okay, for this next question, I'm including a little bit of notes because if you show up to the test memorizing formulas, you could go through some of these questions really quickly. And what we have here is we have this logistic differential equation, and we want to know if the initial population is here, what is the limit as t goes to infinity of p of t? So in general, the limit as t goes to infinity of p of t, this refers to the carrying capacity. So it's like, what's happening as time goes on? What's the cutoff value here? So what is our carrying capacity? If I look at a little sketch of these, p of 0 is 3,000. Like, we're essentially looking at a graph that's something like this, and we want to know, like, what's the cutoff value here? So that's our carrying capacity. And if you know your formulas, then you really just need to get this to match this shape here. So I would factor out a 2 so that I'm leading with a 1. And that would tell me that dp over dt equals, and we're factoring out the 2. So I have 2 times p, and I have 1 minus p over. But if I factor out a 2, that's going to make this into 10,000 on bottom. Just making sure I'm writing enough zeros. Notice if I redistribute the 2, it sends me right back. So then the carrying capacity L is just this value here. So in this case, L is equal to 10,000. Now, me personally, I forget this formula all the time. So another way of thinking about this question that's also very good, it's very conceptual, is you have to think about what happens as time goes on to the shape of this logistic differential equation. Well, the logistic differential equation is here, and here's the actual curve. But notice as time goes on, the slope of the curve is heading to 0. So that means the limit as t goes to infinity of p of t is whatever that y value is, dp over dt. As this happens, dp over dt is heading to 0. So if we set dp over dt equal to 0, that gives us 0 equals p times 2 minus p over 5,000. And notice here that the first factor, p equals 0, that also makes sense. When the population is heading to 0, the slope is 0 on this part of the curve. But now this factor tells us the value of the population where the slope also returns to 0, and that's the carrying capacity. So if we set 2 minus p over 5,000 equal to 0, this gives us 2 equals p over 5,000. And if we cross multiply here or do the algebra, this tells us that p equals 10,000. So this also tells us the carrying capacity, but this is way more logical and easier to remember than that formula I wrote out at first. So this one, either way, is going to be choice E. So for this question here, we're told that this Taylor series converges to f of x for all real x. So we have f of x is equal to the series from n equals 0 to infinity. We have a sub n times x to the n. And we want to find f prime of 1. So here we're just going to use the calculus for Taylor series. We're just going to take the derivative of the x to the n part. And all the terms with n are going to remain unaffected. We have n times x to the n minus 1. And now we want to find f prime of 1 specifically. So we're going to plug in x equals 1. So we have the series from n equals 0 to infinity. We have a sub n times 1 to the n minus 1. But this piece is just going to be equal to 1. And when we look to the answer choices, it seems like our answer choice is not going to be there, that we have n times a sub n, but the n equals 0 doesn't match the n equals 1. But the reason why they are the same series is, think about it. If I start at n equals 0, I have 0 times a sub 0, which cancels out, plus, and then we have a sub 1 times 1 plus a sub 2 times 2, and so on. This just continues. So notice here that this is the same series because this starts at 1 times a sub 1, which matches this first term because this term canceled out here. So this one's going to be choice D. Okay, so last question here, L'Hopital's rule. If you want to plug in real quickly here, you could see that we have the integral from 1 to 1 of e to the t squared dt, and that's equal to 0. And if you do 1 squared minus 1, that's equal to 0 on bottom. So since the limit of the top and bottom is both heading to 0, the limit right now is an indeterminate form, so we can use L'Hopital's rule. We don't have to write out a formal explanation, but just know by L'Hopital's rule, this is equal to the limit as x approaches 1, and we're doing the derivative with respect to x of this integral here over the derivative with respect to x of the stuff on bottom is just 2x. Now this, we're using the fundamental theorem of calculus part 2, that when it's just a constant to x, these in a sense just cancel out, and it's going to make the limit as x approaches 1, and we have e to the x squared over 2x. So this we could just evaluate by direct substitution now. We have e to the 1 squared over 2 times 1, which is just e over 2. This is going to work out to choice C.